Go ahead and get that thing going so we can make sure it's going to work. Kayla McClellan. You get the reference to the Scottish student? The Scottish play? You reckon? Okay. Cody Wade Young. Dustin Taylor. Dustin Taylor. Oh. Yeah, you. Garrett. Say again? Oh. Chris Stuck. Cyrus. Jeffrey Snowden. Say, is Jeffrey Snowden? Cade Bridges. And Giancarlo Urbina. And Chris and Jeffrey are still out here. Oh, yay. Isn't that nice? Jeffrey Snowden. Boy, ain't it? Yeah, as I was saying, as a class, you did very good. And several of you were markedly improved over the first exam. So there's hope, yay! Now, let's get started on today's lecture. I'm going to start by asking any of you, has any of you ever done any archery? Shot a bow and arrow? Raise your hands. Okay. Let's do a little mental exercise. Two people stand side by side, each with an arrow. One person fires his arrow level to the ground out of a bow. Say a 64-pound draw bow. And the other fellow holds his arrow level to the ground and simply drops it. And if they both release their arrows at exactly the same moment, which one will hit the ground first? Don't everybody shout out at once. "64-pound bow, how much does an arrow weigh?" He's firing it level to the ground. This is the one that's fired. This is the one that is simply dropped. After a certain amount of time, this one will have fallen this far. This one will have launched out horizontally, and after a certain amount of time, will have fallen the same distance. Sometime later, this one will have fallen to here. And the same time, the one fired will have fallen the same distance. The point is, both arrows will hit the ground at exactly the same moment. The only difference that the bow will make is how far downrange the shot arrow will travel before it hits the ground. Okay? We're going to do a lab this week called projectile motion. And one of the first experiments we're going to do is calculating if you we're going to accelerate a little ball bearing down a ramp and measure its velocity as it rolls along the flat table. And then using that horizontal velocity, you're going to calculate how long it's going to take that marble to fall to the floor, and then using the horizontal velocity, calculate how far out the ball will travel before it hits the floor. Just a little preview of coming attractions for what our lab for Physics 1 is Thursday, right? Yeah. So, little preview of coming attractions for Thursday. Remember our kinematic equations? And what is the one rule that that must be true? What has to be true in order for them to be valid? Were you raising your hand or stretching? Oh, somebody raise their hand. Who can answer that question? Well, you weren't called? Okay, look, everybody, I'm going to have y'all all afraid to breathe. No, don't call on me, please. You look like a room full of deacons when the preacher's getting ready to call on someone to open in prayer. Well, no, not me, don't call me. What is the condition that has to be true in order for our equations of kinematics to be legitimate, to be valid? No, that's from algebra. That's both sides of the equation you have to do the same thing to both sides, but say? Bingo. Acceleration has to be constant. That, as long as the only acceleration that the object is experiencing is the acceleration due to gravity here on the surface of the Earth, then that acceleration is going to be constant. Now, that means that when we start talking about motion in 2 dimensions, we are going to restrict our cases to cases where the horizontal acceleration is 0. Okay, so we're going to be talking about balls that are thrown, or balls that are batted, or marbles that roll off of the table. The point is that we are going to be examining their motion only in that time interval when the horizontal acceleration is 0. That doesn't mean their horizontal velocity will be 0. The horizontal acceleration will be 0, and the vertical acceleration will still be constant. So if we're talking about a ball that was hit with a bat, we're only talking about the ball after it leaves the end of the bat. If it's a ball that's been thrown, we're only talking about the ball's motion after the pitcher releases it, and before the catcher catches it, or before it hits the ground. During this time, it will be under constant acceleration in the vertical axis only, and we can then legitimately analyze it with our equations of motion. Now, think back to our last lecture. We learned about vectors and how to add them and subtract them, and we didn't really learn how to multiply them yet, but what we did learn is that when we're talking about the Cartesian coordinates, the rectangular coordinates, the vectors can actually be dealt with independently. And that's how we're going to introduce these two-dimensional equations of motion, or motion in two dimensions. Make sure I didn't have any. That's true. Not sure why that's in this book, but okay. If you'll look on page 59, you'll see a 3-4. Page 59, you'll see a multi-exposure photograph in figure 319 that shows the what I was just talking about with the fired arrow from the bow and the arrow that was just dropped, and how both hit the ground at the same time. It shows the motion of a ball that rolls out horizontally and falls, and one that's just released and falls straight down. And it shows how the vertical acceleration is exactly the same in both cases. The only difference is the horizontal component of motion in the yellow ball. Now, we looked at how to add vectors. You know what? Let's let me see if we've still got these equations of motion somewhere. I think it's handy to have those written down to where you can look at them, especially when you're solving problems. Oh, and you know what? What did I forget to do? Anybody? Say again? No. No, when I started the class, what did I forget to do? Well, that's true. I forgot that too. I'm forgetting all kinds of things. Everybody sign in. Forgot to ask y'all if anybody had questions about the homework assignments y'all were turning in. Does anybody have any questions from the homework assignment y'all are working on? And those are the standard kinematic equations we know and love from Chapter 2. Now, we're going to work in two dimensions. And as I just pointed out, we can treat the motion in the horizontal axis and motion in the vertical axis independently of each other. So, let's take as an example, let's work through the example of this fictional arrow that I talked about. Let's say that one arrow is launched at I don't know, how fast do arrows tend to go? 50 meters per second, does that sound reasonable? Now this one is released with an initial velocity of 0. We can determine how long it's going to take both of them to hit the ground right here. Now this one has got 50 meters per second velocity, so before we proceed, let's clarify this. This velocity, this initial velocity is horizontal, and it's 50 meters per second. As a vector, that would be v naught of 50 meters per second I plus 0 meters per second J. Remember, two components, the horizontal and the vertical, and they're separate. They're independent. This one is 0I plus 0J. And we're going to call this one 1 and this one 2. So, if we're going to be looking at the vertical motion, then we probably want to clarify that equation. So instead of x, we'll write it as y equals y sub naught plus v, what I call y number 2, we'll just plus v sub y naught times t plus 1/2 a sub y times t squared. But what is the acceleration? It's the acceleration due to gravity. So it's instead of a, we're going to call it g. And since it's going down, we're going to call positive y up. And so g will be minus g. And this becomes minus 1/2 g times t squared. That's the y component motion. What's the x component motion? Well, it's the same thing. X equals x sub naught plus v sub x sub naught times t minus 1/2 g times t squared. What's v sub x sub naught? It's 0. V sub, and for this one, for the dropped arrow. V sub x sub naught for the fired arrow is not 0. So,
it shows that equation for y equals, but they don't have a time on this one. Is it just because they got lazy in writing it?
No, that's a typo. Yeah, what page is that? 58. If you'll look at the bottom of the paragraph on page 58, you'll notice that they put that equation, but they left off the t for v sub naught. There should be a v sub naught. That should say v sub naught t, not just v sub naught. That's a typo in your book. So if you want to write it in, go ahead. So how long is it going to take either one of these arrows to hit the ground? Well, let's look at the dropped one because we don't have to worry about any horizontal motion. And we can just write y is equal to the initial position is at whatever height it is. We'll call the height, we'll call the starting point 0, so we'll get a negative value of y when we solve for this. But just, you know what, just to keep you frosty, let's say, let's not make the initial height 0. Let's say the ground is 0. So what would the height then be? What's an average height for someone's arm length? No, height above the ground. 4.5 feet? So what's that? Let's say 1.5 meters. I don't know how close that is, but let's say this is, and that's a V, not a Y. Let's say this is Y equals 1.5 meters. This at the ground is Y equals 0. So we know its position starts off at 1.5 meters. We know it has 0 velocity, and then it's equal to, it's accelerating, you know, its motion is 1/2 g times t squared, where g is 9.8. So we want to know how long it takes to get to y equals 0. So we set the equation equal to 0. If we wanted to know how long it takes the arrow to fall 1 meter, which is nowhere, say, 1/2 meter, then we know it starts at 1.5 meters. Once it's fallen 1/2 meter, what height will it be at? Come on, this isn't a trick question. If it falls 1/2 meter, then it'll be at y equals 1 meter, and we would set this equation equal to 1 meter and solve for how long it takes to fall to that height. Since we are looking for how long it takes it to get all the way down to the ground, where y is equal to 0, then we're just solving for y equals 0. What if we had stayed with the way I started, where we define this as 0 and the ground at minus 1.5 meters? Then how would we write this equation? Exactly, we would just solve for minus 1.5 meters. But then at that point, y sub naught would be 0 meters. Okay? Does everyone see how this works? Okay. Well, we solve for t, and we get minus 1.5 meters is equal to minus 4.9 meters per second squared times t squared, because I subtracted 1.5 meters from both sides of the equation. Now I divide by 4.9 and I get minus 1.5 meters divided by minus 4.9 meters per second squared is equal to t squared. Look at the unit analysis. This meter divided by that meter cancels out, but the per second squared gets inverted, goes back up on top, and we end up with, what's 1.5 divided by 4.9? What, 0.21? 0.31? And if you take the square root of both sides, .55. Well, that tells us how long it takes for the arrow to fall from here to here is a little over half a second. Now, where is the arrow going to land? Where's the arrow that was fired going to land? To find that, we solve the horizontal motion, where x is equal to x sub naught plus v sub x sub naught times t minus or plus 1/2 a sub x times t squared. Well, we don't know what x is going to be, so that's what we're solving for. But we do have to know what is x sub naught, and so let's say that it starts at x equals 0. That takes out that term. What if we were firing from 10 yards behind the firing line? What if 0 were here and this was x equals minus 10? Then this initial x position, x sub naught, would be minus 10, not 0. Okay? I'm emphasizing this because I want you to wrap your minds around the fact that we don't just go in and start randomly setting things equal to 0 without thinking about how it affects the equation that we're about to solve. Okay? So when you're taking an exam and you see this equation and it suddenly looks big and scary, don't panic and just start setting things to 0 hoping it gets simple. Think about what you're setting to 0 and why. Think about what you're solving for and why. So let's keep this one simple, and we'll leave x. We'll set x sub naught as the 0 point, and that way we'll just get a final result that gives us our total distance. What is v sub x sub naught? So x is equal to 0 plus 50 meters per second times t plus 1/2 a sub x times t squared. What's a sub x? A sub x is 0. There is no horizontal acceleration. So x is simply 50, that's a 5, meters per second times t, and we know what t is because we just solved for it. 50 meters per second times 0.55 seconds. The seconds cancel and leaves us with meters. And what's 50 times 0.55? Say again? 27.5 meters. That's actually pretty good. That was a pretty good estimation on an initial velocity for a bow and arrow. I don't know if any of you have ever hunted with a bow and arrow, but you're not going to try for much over a 30-yard shot, are you? I don't care how strong your bow is. So, we know that when this arrow finally does hit the ground out here, it will happen 0.55 seconds later, and it will hit at 27.5 meters. Everybody see how this works? In order to find out how far it's going to travel horizontally, you got to know how long it's going to travel horizontally. How long will it take to hit the ground? You find that out independently of how fast it's moving or how far it's going. That's actually kind of intuitive in the statement of the question. You want to know how far it's going to travel. The first thing you have to do is find out how long will it fall? How long will it take it to fall? That right there implies that the two have to be independent of each other. Okay? Solve for how long it takes, then how far it goes is just a simple matter of rate times time equals distance. You'll probably remember that one from, did any of you take any of this in high school? Everybody remember the rate times time equals distance? Okay. Now, when you fire an arrow at a deer, you use sights. How do the sights work? Come up here and draw us a picture on the board. How do the sights work? Oh, let's see. Well, let's take a look at this. We'll use 3 colors because most archery sights have your string. Here's your bowstring. Well, let's do the bow in black. Here's your bowstring, or your bow, and your string. And I'm old school, so I use an old wooden recurve bow. None of that fancy compound nonsense, cams and levers for me. Which isn't true, but that's okay. Over here on your bow, you're going to have 3 pins. A blue one, a red one, and a green one. Your actual colors may vary. In your string, there's a little grommet, a little loop, little metal ring that's stuck in between the strands of your string, and it's twisted with wrapped around the edges to hold it in place. It locks it right into place. And there's a little metal clip on your bowstring, so you always put the nock of your arrow in the same exact spot on the string before you draw it. Point is, when you draw this bow, that little hole in the string will line up. You'll pull the string up here, and then you'll put your eye looking right through that little hole. And you'll line up one of those 3 pins in the hole. So, if you line up the blue one, you're shooting in this direction. If you lower the string so as to line up with the red one, you're shooting in this direction. And if you line up with the green one, you're shooting in that direction. And I drew the blue wrong. The point is, depending on which one of those pins you line up with, will determine how far you're elevating the arrow above the horizontal. Each one of these pins then is set for a particular distance or range. So, you get more distance by elevating the bow and shooting at a positive angle above horizontal. What if you were trying to shoot something closer than 27.5 meters? Then you'd have to shoot lower and get to hit the ground before the arrow has time to travel 27.5 meters. So, let's now look at how would you solve for this projectile motion, where your object, your ball, your projectile, your arrow, whatever you're launching, is fired at an angle, not just horizontally. Well, let's see. Y sub naught, we're still going to call 1.5 meters. And X sub naught, we're still going to call 0 meters. Okay? The velocity, we're firing the same arrow from the same bow, so its initial velocity is going to be the same. 50 meters per second. But now, it's going to be fired at some angle theta. Okay? Yeah. Now we still have our acceleration. So let's say our initial position, P sub naught, is X sub naught, Y sub naught, which is 0, 1.5 meters. Our initial velocity, V sub naught, well, it's still 50 meters per second at an angle of theta. Let's say theta is, what's a good angle? What would be a typical angle you might shoot at if you're hunting? 15 degrees, 20 degrees? Let's use 20 degrees. Say again? No. Yeah, that's why you went to all the trouble of lining up those little pins on your bow, right? Okay. Well, now we've got to go back and convert this into rectangular form. How do we do that? We know that it's going to be V sub X sub naught I plus V sub Y sub naught J. What is V sub X sub naught? What's the initial X component of that velocity, 50 meters per second? Come on, you all aced the lab last week, and we just had this lecture on Friday. Anybody? No? It's the sum of two vectors, v sub x sub naught and v sub y sub naught. What is the projection of that 50 meters per second vector onto the x-axis? What is this length? Say again? No, 1.5 meters is the y position, the initial position in y. The horizontal component of the velocity is the magnitude of the vector times the cosine of the angle. Plus the magnitude of the vector times the sine of the angle. The vertical component is the magnitude times the sine of the angle. So the initial vector would be written as 50 meters per second times the cosine of the angle I plus the sine of the angle J. Or let me say 20 degrees. So somebody with a calculator, what's 50 times cosine 20? 46 point what? 0.9 meters per second I. What's the vertical component of that initial velocity vector? 17.1 meters per second J. That is our initial velocity vector in rectangular coordinates. Because now that we're dealing with orthogonal components, we can deal with them independently, individually. Okay. So we've got the initial position. Now what is our acceleration vector? Say again? No, we have acceleration. And it has to be constant. What's the horizontal component of our acceleration? Yeah, how much horizontal acceleration? Now, not while the bow is being fired, but once the arrow leaves the bowstring and it's in free flight, the horizontal acceleration becomes 0 meters per second squared I plus what? G J, which is 0 meters per second squared I minus 9.8 meters per second squared J. And that's constant. which is important. Otherwise, if our acceleration vector was not a constant, what would that mean? Then none of our equations would be valid. Exactly. Okay, this is our problem. This is our initial conditions. We've got an arrow that's been fired at an angle of 20 degrees with an initial velocity of 50 meters per second at 20 degrees. How long will it take it to hit the ground? Y equals y sub naught. Just before we do anything, let's just write the equation that we're going to be solving for. Y equals y sub naught plus v sub y sub naught times time, regardless of what it says in the book, plus 1/2 a sub y times time squared. What y are we looking for? We're going to solve for t. We want to know t when y equals what? When y equals 0, well, what is our initial y position? P sub 0 at y is plus 1.5 meters. So we plug that into our equation. What is our vertical y, initial vertical y velocity? Plus 17.1 meters per second. Times t. And now what is our y acceleration component? Minus 9.8. So minus 9.8 meters per second squared over 2, 1/2 a t squared, times time squared. So we're going to solve 0 equals 1.5 meters plus 17.1 meters per second times t minus 4.9 meters per second squared times t squared. What do we have to do? The dreaded, everybody say it out loud together. The dreaded quadratic formula. In this case, t will be equal to minus b plus or minus the square root of b squared minus 4ac all over 2 times a. Did I get that right? Oh, look at me. Hoorah. Okay, well, what's b? This is not in standard form, right? What we're solving for is 0 equals minus 4.9 t squared plus 17.1 t plus 1.5. That's, you always put the function or the formula, the equation, in descending order of exponents to get the right coefficients. That means this is A, this is B, and this is C. So, T equals 17.1 plus or minus the square root of 17.1 squared minus 4 times minus 4.9 times 1.5 minus 4AC, all divided by 2 times minus 4.9. Say again? Where? Is it minus b squared? Or is it plus b squared?
No, minus B. No, like minus B. So the first 17.1.
Oh, this should be negative? Oh, minus. Oh, I see. Yeah, I did. I wrote it right and then I wrote it wrong. Right. So is this right now? This 2A. Yeah, that's why I said you got to put this in standard order from the highest to the lowest exponent. Otherwise, you'll get the wrong coefficients. You'll put all the wrong numbers in all the wrong places and get all the wrong answers. So now when we solve for that, somebody with a calculator do the arithmetic. Minus 17.1 plus or minus, what's the square root of all of that? $17.1 squared minus 4 times 4.9 negative times 1.5 is minus 29.4, so that's plus or minus 321.81. And the square root of that divided by, everybody should know what 2 times minus 4.9 is because it's what we started with before we divided it by 2. 9.8. No, is it? Yeah, it is. No. Yes, it is. Negative 9.8. All right, what's the square root of 321? 17.94. So we get minus 17.1 plus or minus 17.94 divided by minus 9.8. So minus 17.1 minus 17.94 is minus 35.04 divided by minus 9.8, or .84 divided by minus 9.8. So that gives us two solutions, which you expect from the quadratic formula. And those two solutions are, and I put my calculator away too quick, 3.58 seconds, positive 3.58 seconds, or minus 0.085 seconds. We got a negative result on our quadratic equation. What does that mean? We can neglect it, but why can we neglect it? Say again? Why not? There was no time before you fired the bow? Exactly. Negative time just means relative to t equals 0, it would have hit the ground 85 milliseconds before you release the bow. In other words, what you're doing is you're backtracking this trajectory back down to the ground. That's what the negative result here implies, is that this many seconds before you let go of the bow, it would have been on the ground. This, then, is the meaningful result for solving our problem. And yeah, I see the time, so we'll finish this on Wednesday.